So, in the present class today, which will be our 14th class on the transport phenomena, we will discuss the overall energy balance. So, let us come to our 14th class on transport phenomena. We will discuss today the overall mechanical energy balance. Overall mechanical energy balance. Let us try to understand what is the fundamental basic of this overall mechanical energy balance. The fundamental of this mechanical energy balance in overall form is the first law of thermodynamics. So, its basic is the basics is first law of thermodynamics. So, for a reactor, the overall mechanical energy balance can be given as amount of energy entering the reactor. So, this is amount of energy entering the reactor with a fluid. So, amount of energy entering the reactor with fluid per unit time minus amount of energy leaving the reactor with fluid per unit time. That should be equal to the rate of change of energy of fluid in the reactor minus heat energy absorbed by fluid plus work done by the fluid on the system or the surrounding. So, the plus the work done by the fluid on the surroundings. So, this is our basic philosophy for this overall mechanical energy balance formalism. Now, assumptions. Assumptions. Here you have to assume some assumptions. So, the first assumption is no heat effect, so that this term may be neglected. No heat effect. Now, the no heat effect, no heat exchange. So, this point may be further strengthened. Neither the exchange nor any heat effect is encountered in the reactor as the fluid flows through the reactor. And number 3 is the equation of continuity is being obeyed. Equation of continuity is being obeyed, that means the mass flow rate in, that should be equal to mass flow rate out. So, that is rho I V I A I, that should be equal to rho naught V naught A naught. Now, because all these equations encountered in this overall balance will be interrelated. So, let us try to write at one place now. Now, let us assume rho I and rho naught in inlet and outlet stream. A I and A naught cross sectional area in the right at in inlet and outlet stream. V I at V naught is the fluid velocities in inlet and outlet stream. Let capital V R is the reactor volume and rho R is the average fluid density in reactor. When we are making these notations, so on the basis of this notation, once we apply these notations in their different forms in the equation number 1, you will get the expression for the overall mechanical energy balance. So, come to the formalism. What the formalism is? So, the various energy terms associated with the fluid are: number A, the potential energy. It will be denoted by the letter psi, the Greek letter psi in this case. First is the potential energy. Number B is the kinetic energy. It is denoted by another Greek letter phi. C is the bulk energy. It is denoted as PV, and D, that is the internal energy, abbreviated by letter U. here it is necessary to emphasize that this P and V are the volume, are the pressure and volume, are the pressure and volume per unit mass, volume per unit mass. So, if I am denoting the letter E for specific energy, if E is the total specific energy, that is energy per unit mass, unit mass for the present system, then we can write that is the E is equal to potential energy psi plus the kinetic energy phi plus the internal energy U plus the bulk energy PV So, this is the expression for the total specific energy, that is the energy per unit mass. Now, energy entering, amount of energy entering, the system per unit mass, sorry, not per unit mass, because I have taken the term specific energy. So, that needs to be removed here, per unit time. Energy entering the system per unit time, that is this quantity, let it be EI, that should be equal to psi. First add all the specific energy terms, that is the psi I, phi I, that is for the inlet stream, UI plus Pi Vi into this quantity, that is the mass flow rate, that is rho I Vi Ai. Let it be question number 3. Similarly, energy leaving the reactor, energy leaving the system or reactor system per unit time, that is the energy leaving the system per unit time, that is the energy which will get dissipated by the virtue of this outlet stream, that should be equal to psi naught plus phi naught plus u naught plus p naught v naught, and it should be multiplied by rho naught v naught a naught. Let it be question number 4. Now, let us suppose if W is the work done by the fluid on the surrounding, if W is the work done by the fluid on the surroundings, per unit mass per unit time, per unit mass per unit time, then equation 1, using equations 2 to 4, takes the shape as amount of energy entering, that is the psi I plus phi I plus ui plus pi vi multiplied by rho I vi ai minus psi naught plus phi naught plus u naught plus p naught v naught into rho naught v naught a naught, this minus this, that is equal to rate of change of energy of the fluid in the reactor, that should be equal to delta by delta t rho r into Vr into the specific energy E. So, this quantity will be 0 by the virtue of the assumption number 1 and 2. So, work done by the fluid on the surrounding, that should be equal to W into rho naught V naught A naught. Since the equation of continuity is being implied, I mean assume that the equation of continuity is being followed. So, this and this should be equal with each other. So, we can write Vr is the constant quantity, Vr is a constant quantity. So, taking it out, delta by delta t rho r E, that should be equal to psi I minus psi naught plus phi I minus phi naught plus ui minus u naught plus pi vi minus p naught v naught, okay, minus w, and it whole should be multiplied by rho naught v naught a naught, that is the with the help of assumption this. So, let it be question number 5. This equation number 5 can be further simplified by using the first law of thermodynamics, as that is the change in the internal energy delta U, that should be equal to minus P dV, that is the pressure volume work, integrating from the limit V I to V naught, inlet to outlet, plus irreversible work done. Let it be question number 6. So, let us remove this portion now. In the absence of any energy exchange W irreversible, that may be regarded equal to Wf, that is called the frictional work or irreversible work, because of the fact that work done against the friction, that is work done which have been executed for the combating the frictional resistance, that cannot be recovered. So, it is called the irreversible work in the thermodynamic terms. So, it is regarded in the absence of any energy exchange, this W irreversible is equal to Wf. So, the equation 6 is delta U equal to integration minus P dV integrated from Vi to V naught plus Wf. Sorry. This is Wf, where this Wf is the work done by the fluid. This is for the work done by the fluid. So for an infinitesimal change, that is very small change, for an infinitesimal change, equation 6 can be written as, see, the equation 6 determines, equation C is describing a finite change. That means as you change the volume from the initial volume to the inlet volume to the outlet volume, then you are integrating this term Pdv and you are taking this W irreversible work into consideration, then it will give rise to the change in the internal energy under the specified limit. So, such type of changes are what are known as finite changes. So, this equation stands for the finite change and the expression of the first law of thermodynamics for the finite change. However, in the case of infinitesimal change, the same equation number 6, which stands for the first law of thermodynamics, can be rewritten as du is equal to minus Pdv plus delta W irreversible. Let it be equation number 7. Thus, from equation number 5, from equation number 5, rho r, this quantity may be assumed as constant. So, we can write rho r, Vr d by E by d by T, that should be equal to psi I minus psi naught plus phi I minus phi naught plus u I minus u naught, okay, plus p I v I minus p naught v naught within bracket minus W, that should be equal into whole multiplied by rho naught V naught A naught. This equation, this is the transformed equation for finite change. This is for finite change. On the contrary, if the same expression, if I have to represent for an infinitesimal change, then it takes the shape. And otherwise, this equation can be represented as rho r V r divided by rho naught V naught A naught d by E by d by t, that should be equal to minus delta psi, because of the fact that the potential energy in the outlet stream should be lesser, so that the fluid can flow from a higher region to lower region. So, the psi I minus psi naught is equal to minus delta psi plus minus delta phi plus minus delta u plus d minus PV for this quantity minus delta W. This equation stands for infinitesimal change, or it can be further written as minus d psi minus d phi minus du minus p dv minus v dp minus delta W. Let it be equation number 8. Thus, from the equation number 7 and 8, from equations 7 and 8, it implies rho r V r divided by rho naught V naught A naught. See, here I would like to remind again, capital V stands for volume, small v stands for the velocity. So, please keep in mind in the example also, d by E by d by t, that should be equal to minus d psi minus d phi now du from this expression. So, minus du is equal to plus p dv minus delta W irreversible minus p dv minus VdP minus delta W. So, this can be written as minus d psi minus d phi. So, this will get cancelled out, minus VdP minus delta W plus W irreversible, this quantity. Let it be equation number 9. This equation number 9, it is called Bernoulli equation, for unsteady operation. So, for the unsteady operation, the Bernoulli equation, which is nothing but an overall mechanical energy balance, that at every cross section the sum of the total energy is the constant. So, this equation stands for the Bernoulli equation for the unsteady operation. For steady state operation to happen, steady state operation to take place, which quantity should be 0 in this case? This d by E by d by t needs to be 0. D by E by d by t, that should be equal to 0. So, the Bernoulli equation for the steady state operation can be given as d psi plus d phi plus VdP plus delta W plus W irreversible, that should be equal to 0. This equation number 10 is the Bernoulli equation, Bernoulli's equation for steady state flow. So, if the equation number 7 needs to be written in the terms of finite changes, this is for the infinitesimal change. For finite changes, equation 10 can be given as delta psi plus delta phi plus VdP needs to be integrated from the pressure in the inlet stream to the pressure in the outlet stream plus W plus W irreversible, that should be equal to 0, because this is state function. So, the integration is again 0. So, this is your Bernoulli equation for the steady state for the finite changes. Both the equation number 10 and 11, equations 10 and 11 can be used to evaluate pressure drop in industrial practices. In the cases where work done by this system on the surrounding, by the system on the surrounding is taken as 0, this considering that to be a bottom line or datum line. So, if I am considering this as 0 and if this W irreversible is equal to frictional work Wf, that is the frictional work, then equation 10 is, then equation 10 can be represented as, then equation 10 can be represented as then the equation number 10 can be represented as d psi plus d phi plus v dp plus Wf, that should be equal to 0, delta Wf, plus delta Wf, that is equal to 0. Let it be question number 12. This is for infinitesimal change, and for finite change delta psi plus delta phi plus v dp from pi to p naught, this plus Wf, that should be equal to 0. Let it be question number 13. Now, since this completes your overall mechanical energy balance formalism or the Bernoulli theorem, let us take an example. So, delta psi d psi, that may be represented as GDH, that is the potential energy term considering mass to be unity. So, the d psi is equal to dgh, delta phi, phi is the kinetic energy per unit mass, that is half mv square divided by m, that is equal to half v square. So, the quantity d phi is equal to v dv. So, this equation number equation number 12 can be written as GDH plus VDV plus VDP plus delta Wf is equal to 0. And if I am taking the finite change, if I am taking instead the finite change, for finite change this equation can be transformed as G delta H plus V delta V plus V dP, integrating between the limit pi to p naught plus Wf, that is equal to 0. So, this equation as well as this equation are the two forms of Bernoulli equation for the steady state operation of the fluid flow in the reactor, which is a consequence to the overall mechanical energy balance. So, in the next class we will discuss the different energy balance specific case for the turbulent flow, and we will also put some emphasis on the kinetic energy velocity correction factor for the laminar flow. Thank you.